All right. So you guys just watched Tale of Two Twins. With if you just replace the train with the rocket, then there you go. Right, and you guys saw that rocket twin. Hardly any time had passed from his frame of reference, but Earth twin, a lot of time had passed. He turned into to this old man. Right. Now, if there are different passages of time, uh, the story can't exactly end there. There has to be more to it. Okay, here's what I'm thinking. Suppose it's way in the future, and we're gonna set out and start exploring the galaxy. Okay, so I have Earth here. I'll say E for Earth. Okay, there's someone out here, and we're gonna take off in this rocket. Okay, there's somebody in the rocket. So, oh, we got Earth twin and rocket twin. How about that? Okay, okay. And we're gonna head off for like some distant planet. Way out here called E for planet. Oh, and maybe it's like 10 light years away, right? So distance equals 10 light years. Right? You guys know 1 light year is the distance that it takes light to travel 1 year, right? Right. So just make up a number, right? Let's say this rocket travels like 99% the speed of light. Yeah, it's crazy numbers, but just the exercise, just run with it, right? Right. So if this rocket travels like 99% speed of light, then from Earth Twin's point of view, it would take this rocket a little over 10 years to reach this planet. Right? You guys got that? A little over 10 years to reach the planet. But inside the rocket, Rocket Twin, R for Rocket Twin, right? Remember, he says hardly any time has passed at all. I mean, if he's going like 99% the speed of light, it might be a lot less than that. I have to run the numbers, but maybe like a year or something like that. But how can it take a year to go a distance of 10 light years if you can only travel up to the speed of light, right? Well, remember, these are all relative. From Earth Twin's point of view, he's looking out his telescope. He only ever sees the rocket travel at less than the speed of light. Right? Can never quite reach it. Right? The rocket twin says, no, actually, I went this whole distance in less than the time that you thought it should have taken. So it's not just that there's a time contraction, but there's also a length contraction. This journey doesn't appear to be as far when you accelerate up to those speeds. Right? You guys got that? So let's go add to these equations here. Right. Right, so here's the time dilation that we went over. Right. I was showing a train. I showed you guys the video of Earth twin and rocket twin. So here's the Earth twin's time and rocket twin's time. Right. But it can't be the end of the story. Right, let's jump down to this very last one. It says something about a length dilation. Length dilation. Okay. So this will account for this length contraction. Right. So the distance from say Earth to that distant planet. Right. It's going to appear to become closer. Right. So, right. And something else that also dilates is momentum. Now, Newtonian momentum, you guys remember from last semester, is just momentum is mass times velocity. You guys remember that? Momentum is mass times velocity, right? Right. That's what Newton would have said. And in fact, that's pretty well true as long as your speed is non-relativistic. Right? So, like a relativistic speed would be a significant fraction of the speed of light. So if he's pretty close to zero, zero versus c squared is zero, one minus zero is one, square root of one is one. And oh, yeah, it just boils back down straight to Newtonian mechanics that we've been using all along. Right? What's the fastest that any human has ever moved relative to any other human? I'm going to guess probably like going in orbit around the Earth or some version of that, something to do with like in a rocket, right? But even that, like these dilation factors, like the speed you go for whichever one of these equations you want to apply to is so small compared to the speed of light that it's pretty much a negligible effect, right? So do astronauts like travel through time? Yeah, tiny, tiny, tiny bit, but like it's like a fraction of a second. Okay. Right. So let's look to. I want to do a graph for this middle one, momentum dilation. So let's do this. Right. Got relativistic momentum. Right. So what is your momentum as a function of your speed? Right. Guess that momentum as a function of speed. Right. Well, Isaac Newton said this: momentum is mass times velocity. That's all we used last semester. Right? That's this dashed green line. Right? That's what Newton said. And Newton would have predicted that, oh, if you get up to 3 times 10 to the 8 meters per second, just multiply that by your mass, you should end up having this much momentum. Boom, right there. Right? Einstein says, no, 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 no. In fact, you can never reach that speed. And the closer you get to it, the more your momentum is going to tend towards infinity because you have to divide by this Lorentz factor. Right? Here's that. All right. Ooh, Minkowski. All right. There's a lot of implications of this one. It's a fun one, but just outline the basics here. Okay. Suppose you have this is really a four-dimensional concept. Okay, but okay, our brains can really only think of three dimensions, and I have two dimensions on the paper, so you got to stretch your imagination a little bit. But you guys see these x, y axes? Let's say that those are perpendicular to each other, and they actually represent three dimensions of space, or maybe we just leave out the dimension like height, right? So you got x and y for spatial dimensions, right? Okay. And then this vertical axis, think of this as a time axis. Now, there's some reasons that, guys, what do you get if you multiply speed times time? That represents a what? Speed times time is distance, right? Right. All right. So now all the axes have the same units. Okay, but if you think of it something to do with like time, then the concept is correct. Okay. Right. So if you look at the motion of any particle, it could be you walking around. It could be a light particle, like photon. Okay. There's a motion within this diagram. Um, you know, I want to mention too, it's weird to have time on the vertical axis. We usually do it the opposite way. But let's say you're just standing still. If you're just standing still, then you're moving forward through time, but you're not actually changing your location. So that's just kind of like moving straight up this axis, right? If you're just sitting still, right? If you are in motion, then as time moves forward, maybe you actually are moving around a bit. So you're like moving like out here, right? But what's the fastest you can move? The fastest you can move is the speed of light, right? In fact, light does move at light speed, which is this this line right here. And I dashed it because anything with mass, like you or me, can never actually reach this line, right? And one of the reasons of calling this vertical axis speed times time, like speed of light times time, is that that makes this dashed line specifically at a 45-degree angle. Okay. Right. Now that sets up these cones where these can be anything that have any kind of cause and effect relationship. So the present might be this point right at the origin. Right? And anything that happened before us is going to be in the past. Anything that could have affected us at all in the past, right, is somewhere inside this cone. If some event happened like out here, then that event, like even if you like send a message as fast as you can send it, like at the speed of light, you can only travel at this 45-degree angle, and it would never actually reach this present point at the origin. Okay, so it can't affect you at all. The only thing that can affect you from the past is anything inside this cone. Well, similar idea for the future. If you cause something and there's going to be some effect down the line, then any effect that has is also going to be inside that future cone. Okay, you guys got that too? Okay. All right. Um, ooh, mass energy equivalent. Oh, no. Time out, time out. I want to show you guys another video demo, okay, that maybe explains that a little bit better. All right, so let me switch over here. Switch over.